Okay, so another language aside here, now talking about language syntax of TL Verilog, specifically, not Verilog. A lot of people always ask why I'm using AA instead of just A, and the reason for that is the naming syntax in TL Verilog. So TL Verilog uses fairly strict naming semantics for identifiers, like the pipe signals, they would be called. So a pipe signal starts, as every identifier does, with a symbol prefix, in this case a $sign, and then it's comprised of tokens, pipe and signal, and those tokens are delimited, in this case by an underscore. So these identifiers can have basically three different styles for the delimitation or the casing. So there's the lowercase syntax that's used for pipe signals, and that has underscore delimitation. There's camel case, or strictly speaking this would be called Pascal's case, because every token starts with an uppercase, even the first one. And in TL Verilog, when you're using camel case delimitation, instead of being a pipe signal, it's a state signal. I don't think we're even going to talk about state signals in this workshop, but nonetheless, just to understand syntax restrictions. And then there's also an uppercase, which I also don't think we're talking about. But that's all uppercase characters with an underscore delimitation. So the main message is, when you're declaring pipe signals, all lowercase, underscore for delimitation. You can have numbers in tokens, but always at the end of the token. So this base 64 is fine, but you can't have a number by itself. You can't start the identifier with a number. There are other types of identifiers that are purely numeric, and we'll see that this would be a head by one operator, and you saw that in the earlier example with the counter and with the Fibonacci series. All right, just mentioning Fibonacci series. Let's look at Fibonacci series now in a pipeline. So just taking the circuit that we had, putting that in the context of a pipeline, and not bothering to draw the flip-flops. Right, so essentially the difference here in the code is that I've explicitly given it a pipeline and explicitly put the logic into a pipe stage. So all of the logic in this example is in stage 1. The rest of it is just flops, which are, in a timing abstract sense, not logic. Okay, and this is absolutely identical to what we did before. It's just that before we weren't explicit about the pipeline. Everything in TL Verilog is in a pipeline. So even though we weren't explicit about the pipeline, the logic existed in a default pipeline in the default stage 0 of that default pipeline. All right, so next we've got another lab for you to do. Before you start that lab, though, before I introduce it, I want to go over some procedures going forward for doing the labs. So I've jumped back into the RISC-V Myth Workshop repository that we have for you with all the instructions and everything. If you scroll down here to lab submissions, right, there will be some instructions for submitting each of your lab assignments. And after the workshop, we'll review your assignments and make sure you understand the material and give you certification. So it's important that you submit your assignments. If you inadvertently lose one or two and no longer have the URL for that assignment, we're just looking for evidence that you understand the material. So if you're missing one or two links, that's okay, but we really need especially the later links where all of the knowledge is represented in your submissions. So at this point, the link here is TBD, but there will be, by the time you get to this, a link to a Google form that you can fill out, keep open. Every time you do a lab, you can submit the URL for that lab in this Google form. So a couple procedural things that are really important to keep in mind and make sure you're doing with each lab. This procedure is sort of put in place after some of the recordings were made for the lab assignments. So the videos for the labs are not going to remind you to do these steps. So it's important to get this in your mind now. So for each lab assignment, you should be working in a sandbox with a saved sandbox that has a URL specific to that sandbox. You want to copy that sandbox URL, put it into the form for the corresponding lab, and after you capture it, make sure you go back to that sandbox and clone it. All right. The reason is, if you continue to work in that sandbox, all the changes that you're making in that sandbox will be saved automatically and reflected in that URL. So after you've captured that URL, you want to either close down that window after saving your work outside, or possibly many of the labs build on themselves, so you might be continuing in that sandbox, but you want to instead of continuing to work in that sandbox, you want to clone the sandbox. Get yourself a new URL, a new sandbox, so you're not changing your old submission, and then you can continue working. And make sure, as you're submitting each URL, that the URLs are unique and you haven't forgotten to save a new sandbox to create a new clone. All right. So once you've captured the URL in your submissions, you'll have the URL there. You should bookmark them as well in your browser. You can always open them up again. If you realize that you did something wrong in a prior lab, you can go back and fix it so that it is reflected in what you've submitted. But MakerChip itself doesn't have any nice framework for keeping track of your different sandboxes. It's just through bookmarks, so it's a little bit easy to make mistakes with that. But you can use the browser to bookmark your sandboxes, and again, make sure you're cloning them at the appropriate time, so you're not changing work that you've already submitted for a prior lab. And the last bullet here, I think I mentioned this elsewhere in the videos, but the servers that we have up and running are temporary servers. They will be taken offline. So having the URL is enough for us to review your work and give you certification, but after that's all done, the servers are going to be taken offline. So make sure you've saved any work that you want to have saved outside of MakerChip. Okay? All right, now back to the lab assignment. All right, so now I'm going to give you guys a chance to code up some logic in a pipeline. And this circuit isn't anywhere near as complex as it looks when you're coding this in TL Verilog, where you're focused only on the logic expressions and the timing kind of takes care of itself. So let me set the stage for this example. This would be logic that would be accompanying other logic. So maybe you've got some sort of a computation going on in a pipeline, similar to what we did with Pythagoras' theorem. But this one's a deeper computation. It's over 6 cycles. And there are various conditions that could happen as you're computing the number. So the conditions that we have here are you've got bad input or an illegal operation that you're trying to perform. In stage 3, there might be an overflow condition. And in stage 6, you might detect a divide by 0 in the computation that you're performing. So, these conditions are made up. It's not for any particular computation. But the circuit that you're looking at is simply taking these 4 different error conditions in this pipeline and aggregating them to result in a single error indication. And that error indication would be in stage 6 here, error 3. So your logic is simply taking these 4 different input conditions and ORing them together, right? So in the end, if any of these conditions assert, you need to assert this error 3 signal. Okay, so the blue circles are just ORs, and the red circles you are assuming to be inputs. And you can code up your logic to consume these, just assuming they exist. Maker chip will report that you're consuming a signal that's not assigned. It's a warning. You'll still get a circuit out of it. And Maker chip will just make up values for that, for each of those inputs. And then you can look at your waveform and confirm the behavior. Okay, so again, you can pause the video, take your time with that example, and come back when you're all done.